Vasilis Vlachoudis, who is going to discuss use of FLUKA Monte Carlo in hadron therapy. So with Marcus, we have seen applications of treatment planning in real life, what we have learned the whole week, and now we go again back to Monte Carlo. Vasilis, you are ready to share?
Yes, thank you.
Yes, please.
Jota. So one moment.
In fact, I like to say that we are from the same university with Vasilis, and we just received the message that they celebrate today the birthday of our common professor, Haralambous. He is 94 this year.
Oh, I didn't know. I didn't receive that. Okay. So thank you for the opportunity. I will try to make something which is a bit bold because I made the presentation. You can see my slides, correct?
If you can go full screen.
Yeah, sorry. Because I'm on Linux while I prepared it on PowerPoint. And the reason was initially I prepared a presentation for about 15 minutes, but then I thought that maybe an online presentation would be much better than a presentation, so an online demonstration of the capabilities. So I will try to go quickly through the slides. I will left, there are many things I will not go through, but you can, I left it on the Indico side so you can see it yourself. And then I will move to an online demonstration. So use of FLUKA. Why Monte Carlo? So Monte Carlo in medicine is something that is now steadily increasing in use. You already heard from the previous speaker that they are using Monte Carlo, a giant-based evaluation for a quality assurance of the calculation. Why? Because Monte Carlo, I think, is considered like the golden standard for this kind of applications for simulating this complex environment. You cannot simply rely on simplified models like what the commercial treatment plannings are using. Even I think now also the commercial treatment planning are moving to Monte Carlo. But the real problem with the Monte Carlo is the speed. Of course, to have a full reevaluation of a plan, it takes some time, while a treatment planning system is quite fast. Not only the physics is important, but also to have additional things that are specially adapted for the medical applications, like biological-based scoring, like what Marcus was mentioning before, to have directly the RBE scoring, so you can plug in your model, LM, MK, whatever model you want, and then you can get directly the information. To have also the accurate prediction of the secondaries, because if you go for the hadron heavy ion treatment planning, then you will suffer from the tail of the fragments, and you need to simulate it correctly. And of course, if you want to use it inside the clinical environment, you need to have some kind of an easy interface, because with most of the physics programs are typically complicated to use and it's not adapted for these environments. So FLUKA, I will spare 2 slides on that, is a general purpose Monte Carlo code. It's already now about 60 years old. It started at CERN for making radiation protection calculations. Actually, it was for the SPS accelerator during the construction phase. Then it followed let's say, a path several universities have entered. INFN entered dynamically and contributed a lot for the cosmic rays hours. And then from 2003 until 2019, it was commonly maintained and developed by a CERN-INFN agreement. From 2019, CERN decided that in order to, let's say, welcome easier external contributions and to open the code to the community, because it was a closed source code up to that point, we needed a new type of distribution. So from 2020, CERN now is distributing the code with a revised license scheme. So you can still have the single user license like in the past, that you can download the binary from our website, fluka.cern. Or you can have an institutional license where you can have access to the full source code. You can recompile it and modify it, of course, respecting always the license condition. Then there are various other nuances. I want to strongly emphasize that we have a very lively community, and if you go to the FLUKA forum at CERN, we have a lot of discussions on physics, on technical, on the results, on how to do the simulations, and we all try to organize a couple of training courses per year. This period, of course, they are online and they're highly appreciated. We had almost like 200 participants in the past 2 courses. FLUKA capabilities extends from, let's say, from the cosmic ray environments, from peta eV energies down to kilo electron volt for charged particles, a few hundreds of eV for photons, and for milli electron volt for neutrons. It has multiple capabilities for ions, running coupled, biased or analog simulations, magnetic fields, medical applications, complex geometries, and a lot of built-in scoring. So you can do a lot of things without the need of writing any code at all. So you just write an input file and you run it. One slide of a few typical day-to-day cases that we use here in our group at CERN to resimulate the environment, the radiation environment in the big experiments, like in the Atlas that you can see on the left, or an LHCb on the top right, doses on the BLMs and to be used for tuning the machine, and so on. So on the bottom right, you see a fraction of the 0.7, which is probably the, let's say, the hottest region on the LHC tunnel. Now, additionally, we have one of the most advanced interfaces that exist for Monte Carlo codes that allows you in a complete working, it offers a complete working environment. So with a few clicks and a very nice interface, you can build complicated geometries, complicated inputs, and do everything without the need of leaving the environment or to know how to write the input files. It's very easy to use. In the past years, we have spent quite some time, despite this is not our main, let's say, working, what's called the main line of work at CERN. We are mainly focused on the accelerator complex, but since there were a lot of strong interest from the medical community, we spent quite some time to enhance the machinery that we have and to try to make it as simple as possible to simulate, let's say, medical hadron therapy plans. So now FLAIR is able to import practically all the DICOM files that you need. The DICOM is the standard format for in medicine. So we can import the CT scans, MRI scans. We can convert the CT scans to materials and input inside FLUKA using the Snyder parametrization. We can import the RT structures, so we can score directly on the structures that are inside. And we can import the radiation plan, and so we can reevaluate the full treatment planning. And for that, you don't need practically any programming or file editing skills. It's just a few clicks. I will show you in the demo in a while. Here are some examples of that. Here we had a PET scanning. The patient was injected with a gallium-68 as a tracer. So we got it on the PET output of the gallium tracer. So then we could import it as an extended source inside FLUKA, including also the DICOM, the CT scan, let it decay, and with a few clicks, we can do a full nuclear dosimetry, the dose that the patient received in various organs. We have added recently into the code also the biological oriented scoring, as I said before. So if one is able to provide the alpha beta parameters of the linear quadratic models, instead of getting a physical dose or LET, he can get directly the final cell survival line, which we typically used in the past cases to make a treatment re-evaluation, especially for quality assurance, because the commercial treatment planning tools are good, but they're based on simplified models, while here we can have a full detailed simulation. And on top of that, we can try to do some kind of sensitivity studies, like, for example, what is the effect of the calibration when we go from Hounsfield units to density, how accurate the material composition is going to affect the dose distribution, the impact of the scoring, the grid. For example, the RT structures, they do not match the scoring grid, so then you have to make some assumptions, and all this quantization add additional effects that can be important for them. And the list goes on and on. Maybe just one last slide before the demo. This is also the capability to do full PET simulations. So we have already pre-existing templates of several commercial scanners. So you can import your scanner. And what I'm showing here, we have this commonly used DG mouse. This is a PET scanning of a mouse, a digital mouse. And importing it directly inside the micropet, you can do the full simulation, calculating, getting the coincidence file, the sidogram generation, and from there, we're trying experimentally to play with various reconstruction capabilities. And there was also, in the past, we tried also to do some kind of treatment planning reoptimization, but we have something working, but it's not distributed for the moment. So let me go then for the online demonstration. So let's fire up a flare. So this is the main interface of FLUKA. Here you can do practically everything for the normal simulation, but for the medical, let's import one of the predefined templates that's called voxel that will allow us to import a voxel geometry. For the moment, it's empty. We don't see anything. But if we go to the DICOM tab, we can include, let's include a data set here. So now he found all the DICOMs in the directory, in the subdirectories that are matching for this patient. We can select all of them and he will try to analyze. So you saw now that we have a CT scan, the RT dose, the RT plan, and RT structure. We can, there is an online editor here of the DICOM, so we can modify parameters, inspect, edit, or even anonymize. We can view the slices, like in the RT structure here. And if we go to the voxel, he will load a file that will contain the conversion from Hounsfield units to materials. The materials are included already in the predefined database of FLAIR. And optionally, we can even convert specific structures to give them some specific material. We can say, for example, everything outside the CT scan, outside the skin, we can give it to vacuum, like most of the commercial treatment planning systems are using, instead of having the arrow, so we can see the effect. By giving a name, let's say, I don't know, whatever, foo, and we click the voxel, so it will take a few seconds to process, first to import the file, then process all the RT structures and convert them in a format that FLUKA can understand. And after this step, we can already visualize the geometry, the scan, and we can import then the beam information. Let's wait. So if I add the geometry of the scan here in the input, so we can see clearly now the CT scan that is imported inside FLUKA with all the material conversion and so on. We can continue by adding the planning. So here I have two plans, one for 74 gray and the other for 54 gray. Let's take the 74, and we can ask him to create a plan. This will create all the spots that are existing inside the plan and the various beams as beam cards of FLUKA. So it created some huge files containing several thousands of lines that contains all the beam cards. And after that, what you need is simply to run your calculation. You can select the number of CPUs you want to submit it. You can maybe create a new plan. We can select which beam we want to simulate, the number of CPUs, and we click start and it will start. It will take probably a few minutes, depending on the number of primaries that you put. But let's see directly the results that I have already run just a few minutes before the presentation. So I'm loading exactly the same input file and the results that we get out of the simulation. And here you see the beam one hitting the patient. We can go a step further, and then we can try to compare it with what was predicted by the commercial treatment planning system. So with the RT dose, if we go to our viewer here, we have on one side the RT dose from the commercial treatment planning system, and this one here, what is calculated by FLUKA. You see the difference here that the commercial treatment planning is assuming vacuum around the patient, outside the skin, while here we have some energy deposition directly also on the vacuum. And here you see the difference that is probably hard to see. Maybe we can enhance it. Let's move it by a factor of 10. So what we see now is amplified by a factor of 10 as difference in the dose. And we can already see also the deviates plots for the various region of interest. I think this is more or less what I wanted to show as a demo. I had to be short in 15 minutes, which is of course not enough time to show all the capabilities. But what I wanted to say is that in the past years, we have invested quite some time in the part of the medical capabilities of the code. And I think we are in a situation that anybody can download freely the code, and in a few let's say minutes, you can have a full treatment plan reevaluated and to ensure the quality assurance.
Thanks very much, Vasilis. Indeed, we had no time to do a proper hands-on. We have a loaded program this today. There is one question, if you can. Oh, this is a long answer.
This
yeah,
much longer. Okay,
yeah.
I can briefly state what FLUKA and Jean say on the first, on their introduction to the code. FLUKA, what we say is that it's probably, let's start from Jean, but Jean claims that it's a toolkit. So it's a library that gives the capability to the user to plug in models, and you have to write a C++ program in order to put all the components together. So it's your responsibility to ensure that the various components, they are talking to each other and they are talking exactly with the same precision, the same parameters. But in the end, it can perform the same things. In FLUKA, the philosophy is completely different. We think that the physics is only one, so we offer only one model. We don't have alternative models that you can check. You have a few knobs and switches that you can fine tune. And the whole concept is based on microscopic models in order to have predictability when you don't have data. Both are good codes from CERN, and but okay, the question is can go on.
Yes. They can as well check the documentation of the two programs. Yeah. Thanks very much for your input, and thanks very much to everybody that contributed so far